Gravitational potential energy is also really important in skateboarding. The gravitational potential energy is calculated using the equation mgh. Gravity is especially important for the ramp tricks, in which skaters try to optimize the amount of gravitational potential energy they can convert to kinetic energy. By using well-designed ramps, skaters can minimize the loss of energy to non-conservative forces like friction, and therefore maximize the amount of kinetic energy they have to do really extreme tricks.
Another less commonly discussed type of energy involved in skateboarding is chemical potential energy. A lot of the energy involved in skateboarding comes from the pushing action of the muscles of the skater. The energy to do this comes from the energy in chemical bonds that are broken when food is metabolized. Chemicals like ATP hold a great deal of chemical potential energy, and that energy is used to power the muscles to push the skateboard, thus converting the chemical potential energy into kinetic energy.
As different forces interact with the skateboard, energy is transferred between kinetic energy and potential energy. Beyond the world of textbook problems, friction also transfers mechanical energy into sound and heat as well. Every single trick or action on a skateboard transfers energy from one source to another, and the careful regulation of energy is essential in order to achieve any desired motion.
Momentum is a way to quantify how much an object is moving. In simplest terms, momentum is calculated by multiplying the mass of the object and the linear velocity of the object. It is measured in kilogram meters per second, which makes sense considering the units of measurement that you have to multiply in order to find the momentum.
A change in the momentum is called impulse. Since the mass of an object doesn't tend to change very often while skateboarding, most of the impulses that occur during skateboarding are due to a change in velocity. Since the mass remains constant and the change in velocity is what causes the impulse can be solved by multiplying the mass times the change in velocity. A change in velocity indicates the presence of an acceleration, which exists due to a force. As a reminder, F equals ma, and in order to account for the extra seconds in the denominator, we can multiply by time. In other words, we can alternatively solve for impulse by multiplying the force and time.
This is pretty straightforward in normal cruising, and this simpleness is the ideal. However, I'm pretty freaking clumsy, so I tend to collide with rocks, sticks, and other things, which causes changes in momentum for the individual objects involved in the collisions. However, within a closed system, momentum before collision is equal to momentum after collision. Even though impulses are exerted upon individual objects in the system, the momentum of the system remains constant.
In this video, the skateboard stick system has an initial momentum of the quantity of the mass of the skateboard plus the mass of the sticks times the initial velocity. Though this is technically an open system that is affected by the forces of friction and the normal force of the curb, we are going to treat this situation like an explosion. Initially, the two objects in the system move together, but the force, which we're pretending is internal, causes them to move in different directions. Again, assuming this is a closed system, momentum is conserved, so the sticks move forward at a faster velocity than the skateboard stick system initial velocity because of the fact that the net momentum continues to move in the same direction and magnitude after the collision, and the sticks have to, quote-unquote, make up for the fact that the skateboard is now moving backwards. Explosions are one type of collision, but there are also elastic and inelastic collisions. Elastic collisions involve situations in which there is no change in kinetic energy during the collision. In real life, true elastic collisions don't really exist. All real-life collisions are at least a little inelastic, which means that there is a change in kinetic energy during the collision. The collision shown here is mainly elastic, but there is definitely a change in kinetic energy during the collision, so it is at least partially inelastic. Ideally, collisions like these shouldn't happen in real-life skateboarding, but if you're as clumsy as I am, impulses and inelastic collisions do come into play a little too often while skateboarding.
A great deal of the motion involved in skateboarding has to do with the wheels. We're going to look at rotation, starting with rotational kinematics.
All of the kinematic equations that we use in linear motion can be converted to rotational equivalents. Theta, or angular displacement, replaces x or y. Theta is measured in radians, while x and y are measured in meters. Omega, or angular velocity, replaces velocity. Omega is measured in radians per second, while linear velocity is measured in meters per second. Alpha, or angular acceleration, replaces acceleration. Alpha is measured in radians per second squared, while linear acceleration is measured in meters per second squared. In rolling motion, which is what applies to skateboarding, there are some conversions from linear to tangential that can be used to find angular values. These rolling motion equations remain linear, as tangential values are linear, not angular. For position, the linear displacement is equal to the arc length covered by the wheel, which is noted with the letter S. In order to use arc length to find angular displacement, we use something called a bridging equation. The bridging equations are meant to bridge between linear and angular values. For displacement, the bridging equation is S equals R times theta. Using the example from the very first section, we know that delta x is 4 meters, so S is also 4 meters. The radius of one wheel is 0.03 meters, so dividing 4 meters by 0.03 meters gives us an angular displacement of 433.3 radians. The same can be done with velocities and accelerations. Let's look at v0x from our first example again. For velocity, the linear velocity is equal to the tangential velocity in rolling motion. The bridging equation for tangential velocity is vt equals r times omega. We know that our initial linear velocity was 2.5 meters per second, which means that our tangential velocity is also 2.5 meters per second. So dividing 2.5 meters per second by 0.03 meters gives us an angular velocity of 83.3 radians per second. For acceleration, the linear acceleration is equal to the tangential acceleration in rolling motion. The bridging equation for tangential acceleration is at equals r times alpha. We calculated our linear acceleration to be 0.26 meters per second squared, which means that our tangential acceleration is 0.26 meters per second squared. So dividing 0.26 meters per second squared by 0.03 meters gives us an angular acceleration of 8.7 radians per second squared. Just like in linear kinematics, these equations are mainly used to describe motion, not explain it. So you can use this to describe the motion of something like a spinning wheel, which is really important when it comes to skateboarding. Now, let's move on to how rotation deals with forces. In linear motion, force is the product of mass times acceleration, but in an angular dimension, torque is the equivalent of force, and it is equal to I times alpha, which is the angular acceleration, as we calculated earlier. I is really a measure of how hard it is to set an object in rotational motion, and it's calculated by multiplying a special coefficient times the mass of the object times the radius squared, and the coefficient is based upon the shape. For a skateboard wheel, which is a solid cylinder that rotates about its center, the coefficient would be 1/2. A torque is essentially a force applied on the tangent of a rotating object, and just like how a force would accelerate a linearly moving object, a torque angularly accelerates an angularly moving object. Rotational work is calculated extremely similarly to linear work, except instead of multiplying a force and a distance, you're multiplying a torque and an angular displacement. For example, if I set this wheel in motion, which again is 0.03 meters in radius, by applying a tangential force of 5 newtons for an angular displacement of pi radians, I would have a work of 0.47 joules. And again, the measurement for angular work is the same as the measurement for linear work. It's still joules. Yet again, rotational momentum is calculated extremely similarly to linear momentum. In linear momentum, the momentum is equal to the product of the mass and the volume, but in rotational momentum, the angular momentum is equal to the product of the moment of inertia, which tends to stand in for the mass in rotational motion, and the angular velocity, which is omega. Yet again, in collisions, momentum is conserved as long as it is a closed system.
The important thing to note about this unit is that you can really look at a lot of the things that we did in the past as very similar to things that you can do with rotation. For example, in the past we did stuff like work and energy, but we looked at the skateboard as a whole. Instead of looking at the whole skateboard, you're just taking one wheel and seeing how much work or energy is transferred in between, potential energy stored in a person and the kinetic energy that is now in the wheel. You're pretty much taking the same exact concepts and doing very similar math things in order to find the actual equations. It just has to do with the unit of measurement and the actual object that's being considered.
Simple harmonic motion doesn't really apply to skateboarding. There aren't things like springs or pendulums involved in skateboard motion. However, you can look at the motion of the wheels in terms of sine settled graphs, just like you look at the motion of pendulums or springs in terms of sine graphs.
By recording a wheel's motion and seeing how its vertical and horizontal positions change over time, we can graph the positions of both the horizontal and vertical positions and see how those relate in terms of a sine graph. As you can see by these plotted points, the nature of both the change in horizontal position and the change in vertical position over time represents a sine and cosine graph respectively. You can see that there is a phase shift of pi over 2 in between the horizontal and the vertical. The red dots represent the vertical position and the black dots represent the horizontal position. As you can see, there are quite a lot of things that go into the motions of skateboarding. There are both linear and angular aspects of skateboard motion. Thank you for watching, and I hope you enjoyed.